So yes, today, as you have seen in the program, we will have a look, like an introductory look at statistics and machine learning using Python. And yeah, an important thing to mention in the outlook as we start the lecture is like this will not be a lecture on statistics. Actually, I know very little on statistics, so I don't ask me questions on like sophisticated models and like multi-factor analysis on like whatever kind of data. I don't know much. I will actually focus more on what are the tools, like where you should be looking in Python if you want to do like different levels of different degrees of advanced statistics, like simple or advanced statistics. And I will talk a bit about the framework. Yeah, so I will talk a bit about the interface that some of those libraries have, because at least the last one that we will be talking about, which is scikit-learn, as object-oriented interface for doing data analysis that can be a bit confusing the first time you look into it. So I want to explain the concept behind the usage of the library more than actually the procedures that you can put together with those pipelines. But yes, before getting there, I just want to make a recap of the functions that we up to here we already encountered on descriptive statistics, so-called, which include like functions for computing mean, medians, medians, standard deviations, all those sort of like descriptive quantities that you can be interested in on distributions. And all those simple functions are already implemented at the level of NumPy, which is like the library that we have been most extensively used so far. And like they have perfectly good implementations of the functions, and you actually do not need anything more sophisticated than just NumPy, like different moments. The moment you start require statistical tests, those are actually things that you will not find implemented in NumPy, because NumPy focus much more on just like the low-level computations that you can do on arrays. While here for statistical tests, we actually want a bit more kind of second-level advanced implementations of those functions. And those functions you will find in a library that I don't remember whether we encountered for some things yet, but for sure we have not talked extensively about, which is the SciPy library. And SciPy library is a library for scientific computing, which is like does not just restrict limits to statistics. In SciPy you find functions for Fourier analysis, algebra, like advanced algebra optimization, like things that are not implemented in NumPy but are still kind of widespreadly used for any kind of scientific computing. And among the many things that you will find in the very large SciPy module, there is a sub-module which is the stats module, where you can actually find basically functions for all the, let's say, simple statistical tests that you might be wanting to perform on your data, okay? So if you need to do, I don't know, one sample test of any kind, like normally distributed data, so like t-tests or like Wilcoxon tests, those are all implemented in the stats library. So you import stats from SciPy, and then, of course, like you have to just Google up what is the name of the function that you care about, and those are implemented as functions. So the idea is you will have your data, and usually you have data about distributions of like control, treatment, whatever distributions you have. In this case, I'm just creating data as a simple array of 1,000 elements with a normal distribution, that has a mean different from 0. And so yeah, I can actually just use the one sample t-test to check whether this distribution is statistically significantly different from 0. And this is the result that I get. So the implementation of the test is just a simple call to a function to which we pass the array. In this case is one sample, so only one array. If it's like a two sample test where we are comparing two distributions, we will pass two arrays. The result though is actually is something slightly more complicated than just a number. It is actually an object, which is what is printed here. And is an object that will have some properties, and in particular, like usually what the property that you actually care about is the p-value of the comparison that you just got. There are some others like degrees of freedom and the statistic that were like, which are other numbers that they computing those tests compute, and sometimes you're actually asked to consider them and reporting them. So if you actually need to retrieve the actual value of the p-value, you would have to access the p-value attribute of this test result object that is produced by the function that is implementing the test. Okay, and yeah, there is just a long list of different tests that you can find implemented in this library, but the idea is always the same. Like in this case, I'm generating a second set of data, which is a second NumPy array that has a different mean. And so if I want to compare those two independent samples, I just have to pass the previous array and this array to this function, and the object that is produced is again this object that has a p-value attribute that I can retrieve. Okay. To sample Wilcoxon tests, or if we need pair tests, they work exactly the same. They just require that now those two arrays are assumed to be from pair data, so you are supposed to have the same numbers of elements in the first and the second array. The same if we actually want a non-parametric one from non-normally distributed data. Sometimes we actually want to know whether our data is normal or not, and in SciPy we can also find a function that can test for normality of our distribution. So in this case, I am producing some data that by definition are out of a normal distribution because I'm using the random.normal function to produce them. And if I call the normal test function, this gives me a p-value for how different, how statistically significant, what is the probability of this being different from a normal distribution, which in this case is very low. So it's very high probability this is actually a normal distribution. If we, I don't know, elevate our data to the power of 2, which makes the distribution not normal anymore, I have a super low p-value because my data is not normal anymore. Yeah, there are also some plots functions that are defined in scipy.stats. Actually, this is the only one that it occurred to me to be using in real life. Potentially, if there are other statistical, specific statistical plots, you might find scipy functions for producing them. In this case, this is the quantile plot. I don't know if you are familiar with that. It's the plot where that we usually implement, is this kind of plot that we use to test for normality of the data. Basically, we display our line, each dot is a data point, and on the x-axis we have the theoretical quantiles, which are quantiles each dot is assigned a position over the x, that is the position that it would have if it were normally distributed. And on the other axis, we have just the ordered sequence of points. And the idea of this plot is the farther we depart from the straight line, the farther we are from normality, basically. I butchered this explanation, but this is the concept. The idea is you just assess how much your points are deviated. Usually, if you find just very kind of clear the range, detachment from the distribution, I don't know, we can actually try to make this distribution not normal anymore. Yeah, so this is a distribution that is not normal anymore because I elevated the normally distributed data to the power of 2, and you can see that now we have significant departs from the from the normality, and this plot allows us to show that. But like this is just kind of a advanced plot in terms of like, this is not a, like if you were to be doing this plot by yourself, you would have to like compute some quantiles, scatter the data, interpolate a line, plot the line. Like there are several plotting steps that you would have to, you could potentially generate your plot by yourself. But in the stats library, there is already an implementation of this, of a function that produce this plot, which is this prop plot. So yeah, you can just use it. There are also slightly more advanced statistical models, but I would say you probably won't find anything much farther advanced than a one-way ANOVA after like beyond some level of complexity, like the amount of factors and certifications and whatever. You want to turn to other libraries, but yes, you can find the implementation of a one-way ANOVA, which in this case allows us to understand whether those three data sets come from this different distribution. And again, the implementation is has always this consistent structure of, we call the function, and we have as a result this object that contains the values that we might be interested into. There is an implementation of person correlation, also of Spearman correlation, like any kind of correlation that, like the two kinds of correlation that you might be interested about. So in this case, I am generating two sets of uncorrelated data, and I am computing, sorry. And if I want to compute their correlation, I can use this stats.person R, where I guess I get the R square value as the statistics, and the statistical significance of this correlation as the result. In that case, obviously the data were not that much correlated. In this case, the data are correlated, and so here you can find your your R square for the correlation, and here you find your p-value for the correlation. And remember that if you actually want to, for any reason, you want the float value for the, I don't know, the R square of your data, you want to assign the output of this function call to, I don't know, regression result equal to, and now this is an object, and we want to ask for the p-value attribute, or like the statistic attribute of this object. Okay. Yeah, so this is if you just care about like correlation, but there are also some like other functions for computing. Sorry, this is. There are other functions for fitting lines. So for example, if you actually want to do a linear regression, so you also care about the actual regression, like slope value and intercept value for two set of coordinates. You want to interpolate a line, and like the function from SciPy stats for doing that is line regress. And I mean the usage is quite linear, like we pass the x and the y, which in this case is the data that we produced before. And I don't know, here we are, like this just produced the model. So if we want to look at what was fit, is like this linear regression result, where we have an attribute that is the slope, an attribute that is the intercept, the R value, the P value, whatever, like all the numbers that you might want out of this interpolation, you can extract them from this object. And if we actually want to make the plot for this regression, we want to show like in this plot we are scattering the data, the two data, like x and y as the two data values, and then we are plotting a line, and for this line we actually use the intercept and the slope value from the model that we just fit. Okay. Yeah. So this is for linear regressions, but actually sometimes another statistical operation that you might want to do is to show, like, to interpolate an arbitrary function to your data of any kind. You have a distribution of data and you are interested in fitting a specific function that minimizes the error with respect to that set of data. So I don't know why the spacebar is not working anymore. Whatever. So I don't know. Here I am producing a distribution of points. I actually know in this case that those points come from next decreasing exponential distribution with some noise, but you might have, I don't know, you are collecting those data and you actually have reasonable experimental theoretical background priors to know already which function you actually want to fit to the data that you have. And so to optimize to optimize the function using SciPy, the idea is that first you want to define the function that has to be fit. Usually fitting a function means there are functions that have some given parameters, and you want to find the optimal set of parameters so that that function pass through your data points as close as possible, minimizes the distance from all your data points, okay? And so fitting the function requires, first of all, actually defining the function that you want to fit, and you define the function to be taking as inputs the actual x values for your some x whatever value, which are the x values from which the output of the function will be computed, followed by all the parameters of the function. Okay, so in this case, this is a decreasing exponential function, and a decreasing exponential has three parameters, which are the amplitude of the decreasing exponential, the slope, so the parameter in the exponent that tells you how fast the curve is going down, and an offset for the distribution. And so we actually know that we might want to fit three different parameters to the distribution to actually find the optimal curve that interpolates those points. Okay, and so we have to leave those as kind of free parameters that are accepted by the function that we are optimizing. And we, inside the body of the function, we implement basically we translate in Python the mathematical expression for that function, which in this case is an amplitude term multiplied by the exponential function to the exponent of which we put minus the exponent term times our x value plus c, which is plus the offset of our curve, which is in this case is called c. Okay. So potentially we define this function exactly as we would normally define a Python function of any kind. And then we pass this function together with our the x values for our data together with the y value for our data. Okay, so our original data to which we are fitting the function are a set of points, and for every point we have the x value and the y value. Okay, and so we pass to this curve fit function, which is the function in SciPy that actually implements the curve fit, the function fitting. We pass to this function the function that we want to fit. So we do this funny operation of actually passing a function to a function, but you all remember that functions are objects, and so we can actually move them around as normal variables. So we pass the first argument is the function that we want to optimize. The second is the x values, and the third is the y values. Okay. And what this curve fit function does it actually reads the function that we want to fit, so it knows what are the parameters that it has to be looking for, because those are all the parameters after the first one of the function that we want to optimize. And after the fit, we are left with like two arguments. The first argument is actually, like by convention, is called popt for like parameter optimization, which is the actual value of all the parameters that we are fitting for this function. Okay, so you remember that we had an amplitude term, an exponent term, and an offset term in this order, because we were defining them in this order in the function. And the output that we get is like in popt is actually an array of three numbers, where the first number will be the amplitude, the second argument will be the exponent, and the third argument will be the offset. And if we actually go and now what we can do is to actually look at how good the fit that we just did is. We can scatter our original data, and then on top of that, we can plot. We can make a a line plot, where the x is the x of our data, and now the y, instead of the actual raw data with the noise, is the values that I compute using x, and then the first, second, and third element of this parameter optimization array. Okay, and if I do that, now I get this line, which is like the optimal fit for this specific function given those three parameters. And yeah, we also have some notion of how good the fitness is, and this is the second argument that is returned by the curve fit function, which is this pcov, is the covariance matrix of the parameters, which basically the lower it is, the better the fit that we were producing is. Yeah. So you can actually have a look at the first section of the practicals, where you can just play around with the first simple functions that you find implemented in SciPy. Okay, I will actually correct the first at least, and the second will post the solutions. And yeah, so we can at least read through the rest of the lecture in time. So in this first exercise, you were asked to actually test what you are normally told in classes, which is that if you set a p-value threshold of 0.05, you have a 5% chance of getting a false positive significant result in your test. Okay, and actually, like what we are doing here is something that, in general, if you are not confident on statistics, on your knowledge of statistics as I am, it's actually good to do. Like many times, if you're not sure about like what distribution, whatever is the right statistical approach, a good strategy is you can think of simulating data sets to which you actually run the test that you are thinking for your actual data. So you can read, like, even if you don't know exactly what all those statistics and transformations do, you generate your data, you know, because you're generating them, whether they are from different or the same distributions, and so you can actually test the strength of your pipeline. Like this approach, is a cheap version of what, the fancy name is Monte Carlo methods for statistics, but this is nothing else than just throwing a lot of numbers instead of computing analytically solutions and look at what you get. So this is a fancy Monte Carlo approach to statistical testing. So you do this a lot of times, and you see in which fractions of the runs of your synthetic data you actually get some value or another, and so you can actually know, for example, in this case, what is your rate of true like false positives. I mean, for a p-value, I guess everyone here knows the interpretation of a p-value, but sometimes it's useful for like more like complicated statistical tests that you might end up using. So in this case, the idea was just to go back to our number of tests. So we can put 1,000, and we can say for any number of tests. So every time, like for 1,000 times, we are generating two distribution. Distribution 1 equal to np.random.normal. Let's say mean 0, standard deviation 1. And did I write how many samples? No, I wasn't specifying a number of samples, right? So let's make this distribution of 100 samples and the distribution 2 of 100 samples. So those are exactly the same, like those are numbers which will be different but are drawn from exactly the same distribution. And we can use stats.ttest. Is this the name of the function? Anyone? Ttest ind? Yes. Like this? Yes. These two. This will be a result equal to, we can put all values here. We can say pvals list equal to empty list, and at every entry we can append result dot pval. This should run, right? No? Oh, sorry. This is a mistake that you will never stop doing. And then we can just say fraction false positives equal to, so this will be the sum of pval smaller than 0.05 for pval in pval list. So I'm with this sum I get how many of those comparisons are true, and I divide how many comparisons are true by the length of the list, which is actually number of tests, but whatever. And we can have a look at the value that we get, and this is tantalizingly close to 0.05 for good reasons. Okay. Yeah, I would actually go forward with the lecture, but I mean you get this, and we will post the solutions for the other exercise as well. And yeah, I wanted to have a look at this because I want to talk a bit about the library, which is not this one, the next one, which is potentially useful, but as an interface that can sometimes be confusing. So yes, first, stats model. So up to here, we have seen how to use this stats module from SciPy for the basic statistics. For more advanced models that you might be wanting to fit into your data, like more complicated multi-factor models, we combine like quantitative and qualitative factors, or like generalized linear models, like solid multivariate statistics, but also like fancier like time series predictions, long short-term memory networks, more advanced things. There is this stats models library. Usually, I think the realm in which it is most used is for those kind of multi-factor hierarchical models that sometimes you want to define if you have data set where you have like populations, matrices of conditions, etc. Stat models is a library that is, I think, heavily modeled over R. so it might appeal to people who are used to R, although I have never been using R, so I cannot vouch for what I'm saying. And yeah, I think that also overall from what I read, it has less than what you can find implemented in R. And this is not a kind of statistics that I do very often. So I'm actually like, this specific library, I've never been using it for like a paper of mine. So I cannot be super solid on where it does and where it does not work well. Beware of the fact that like this stats models library, like being modeled on R as ways of expressing those models and like syntaxes that can be a bit funny. I will just show you here an example of what I mean by funny, and then you can discover more by yourself. So yeah, of course you need to you need to install it separate. Like if you want to use it, there are no practicals on it, so you don't have to. But it's not in the installation that that I suggested for the course environment. And yeah, here we are using, like to showcase this library, I'm using a data set that is inside the library. Actually, this is the first time we are seeing it, but you will find it if you read through examples from from some of those statistical libraries. Many times they actually give you also like not only the functions to work on data sets, but they also have some set of example data sets, and they have actually functions to retrieve those data sets. Like they have online an archive of data sets that you can download to have their examples working. So in their examples, every time you find line like this get our data set, where you like this is downloading a specific data set that has a name and is retrieving the data out of this data set. This is what this line is doing. And yeah, it's also like cropping a bit this data set. So basically the idea is, here this is an historical famous data set where a French guy in the 19th century was trying to predict like the tickets sold in the lottery in different regions of France based on like some parameters. Like here the parameters that we're including are literacy in the region, wealth, like just numbers that are indicators of those parameters, plus some, and those are like quantitative parameters. And we have a third kind of parameter where which we could potentially regress our values, which is this region, which is not numerical. This is kind of a qualitative factor in our model. And yeah, here is how we implement a simple ordinary linear model where we try to find parameters that express this dependent variable, so like tickets sold to the lottery, as a function of these literacy parameters, this wealth parameter, and this region identity parameter. And the way in which we are specifying this model is actually a string. And this is why, like I think in R people do it quite often. In Python, this is the only place where I've seen this happening. So in a string, we are specifying the relationship between those parameters. Obviously, those numbers here have to match exactly like letter by letter the headers of the data frame that you're using as the input of this model. And once you create this model, there are a bunch of different models. In this case, like the name of the model is this OLS. I have not put a link, but if you go on the documentation, you will find all possible models that you could potentially fit. And you specify the model in like using this string where you specify the relationship between the columns of your data set, and you also pass the data set as the data argument of this model, and you just fit it. And after fitting it, you get a whole bunch of results, which I hope people who know statistics know how to read better than how I know how to read. But this looks pretty serious, so hopefully you can work with it in your papers. Yeah, so this was stats models. And now I wanted to spend a bit more time on the last library, which is scikit-learn, which is a library that myself know, like I know it a bit better. And this is a library that like in this very fuzzy distinction and spectrum, I would locate as like closer to the machine learning part of the spectrum than to the like statistics, strictly statistics per se part of the spectrum. And this is a library that is useful because it is not just a library, like we will see some of the utilities that this library implements, but it also implements a way of dealing with the data, an object-oriented way of specifying data processing pipelines that is recurrent, and like many other libraries that you will find for like more specific functions, like I don't know, imaging data analysis, electrophysiological data analysis, other kind of like more advanced statistical modeling that pertains to specific scientific domains. Many people tend to adopt for at least part of their libraries kind of the standards that were defined by scikit-learn in terms of how to organize, like how to make those pipelines work. So the reason why I stress this is it is useful not just like we will see a bit of like clustering PCA, some things that we can do with this library, but I care more about you get the sense of you get the way in which those are implemented more than actually how to do PCA or how to do k-mean clustering, which is what we will be doing. Okay. Yeah, closed, like not closed. In like the scikit-learn library is huge. You can really find code for infinite number of things like data preprocessing, data like both things that like actual functions that do clustering, that do linear regression, multilinear regression, decision tree forest, any kind of like you name it, any kind of machine learning technique, super vector machines, like anything you might be using in a machine learning paradigm, you will find it. But you also find a lot of like support utilities for pre-processing your data, splitting your data, and we will see a bit more about this as well. So yeah, the name is, the library is called scikit-learn when you pip install it, but I think this is the first time it happens, but sometimes it does. Sometimes you pip install the name of a library, and then the way that library is called inside Python is slightly different. It's confusing to me, I don't like it, but people have decided that scikit-learn was too long to type, and so you install scikit-learn, but then if you want to use the library, like the library in Python is called sklearn, like shorter. So, and like it has a huge number of submodules, so every time you will be implementing something, you always import stuff from, not just from scikit-learn, but you import submodules. So in this case, we are importing this submodule that is called preprocessing, because this is the first thing that we will be start talking about, which is, yeah, data preprocessing. Many times, if you are, oh yes?
Are pandas data frames faster than NumPy in any way in processing?
I think that, so usually I'm used to use NumPy arrays when you get here to scikit-learn. I would assume that it's probably compatible with pandas as well, but if it does, I would expect it to take a data frame and strip, like, and convert it immediately to a NumPy array. So I don't expect performances to be different using one or the other, but you can test and let me know. I usually just use NumPy arrays if I'm using scikit. Yeah, so I want to show you how you can start overcomplicating even something simple like pre-processing, because sometimes it actually makes sense and is useful. So by data pre-processing, usually you mean like the standard things like, I don't know, the most common thing is data normalization. Okay, you collect your data, and then for whatever reason, I don't know, you want to do principal component analysis, so your data has to be scaled to be normally distributed, like z-scored. Or like you are doing whatever other kind of machine learning approach, and you need your data to be always between, I don't know, -1 and 1, between 0 and 1, or to be like to have a flattened histogram and not a skewed histogram. There are many reasons why you might want to do, like you might want to pre-process your data to like change slightly the distribution that they have. And to do something like this, of course, like we actually already implemented something like, for example, z-scoring. So having your data having mean 0 and standard deviation 1, we already seen how to implement it with NumPy, how to implement it with pandas. Here I show you how to implement it with scikit-learn. Because like here the approach is different from what we were doing. Like usually we were used to directly work with functions or methods of data frames. Here, the pre-processing itself, so the pre-processing operation is codified as an object, okay? So you have to imagine, and this is probably like, and this is what I was referring before as kind of the scikit-learn paradigm. You have to imagine your data processing pipeline as a pipeline that combines nodes that do different things, okay? So you have your raw data, and you have a first node that does normalization of the data, and then you have another node that does, I don't know, dimensionality reduction, and then another node that does clustering of the data, or I don't know, well, clustering is the simplest. Each one of those operations, normally you would call a function that implements it, or like sets of functions that implements it. In scikit-learn, we basically, like, we create an object that represents each of those transformations, okay? So to start simple, for example, for normalization, we have a class that is the standard scalars class, from which we create a scalar object. And that scalar object is the object that in our pipeline represents this step of scaling our data to a standard distribution. And so we first create the object, and note that in the operation where we create the object, like in this case, the data that we want to normalize is this X-train matrix, okay? We don't have to care about what this is now. This is just numbers that are our source data, and we want to normalize them. When we create the object that represents that steps in the pipeline, we are not using our data yet in any way. We have a second step where after we have created this object, we actually fit our data to the object, okay? And actually, we just fit the data. And after we have fit the data, this object has a .mean attribute and a .var attribute, which are for every column of our data, the mean that has to be subtracted and the standard deviation that has to be divided for our data. And then there is a second operation which is called .transform. That is the operation that actually normalize our data based on the parameters that were fit at the beginning, okay? Yes?
What is fit in this context?
Fit is actually finding the parameters that you need for the transformation. In this case, the parameters are super simple because the parameters are just the mean and the standard deviation for each of the columns. In other cases, those parameters will be more complex, like we will see PCA actually fit finds the principal components. Or if you are doing clustering, the fit does is a step that computes the parameter, like all the numbers that you need to produce the transformation that will be produced by that node. So one reason why, for example, this is very convenient is many times when you do machine learning, you actually want to compute, like to optimize a pipeline on some training data. It's very important to optimize a pipeline on some training data set and then use exactly that pipeline on the test data set that you have. It's very important that you actually do exactly the same kind of transformations, the same kind of processes. And in this case, having a scalar object that you have just fit on one distribution and then you apply in the rest of the pipeline makes it very clear that you are always normalizing by the same parameters that you have computed on the trained data set, even when you will be applying them to the test data set. It basically fix all the pipeline in one place. It's also good for like other more advanced kind of representations which we won't touch today, but if you start using the library, probably you might end up using. So it has this kind of peculiar syntax where you feed parameters and then you transform the data using those parameters with the intermediation of an object that represents not actual data, but transformations on data. So this was just the, like in this case, scalar was just a, like this normalizator that would produce this z-score data, but you will find a whole range that optimized for, like, you know, put the min maximum in a range or like whatever. Yeah. So the second thing that I wanted to have a look at is dimensionality reduction, which, like in this case, is just very simple, like the basic principal component analysis, but exactly in the same way as you. Other step. The fact of using this object-oriented representation of the pipeline makes it very simple to, for example, test in parallel different kind of, for example, assume that you want to perform the same kind of clustering or regression, testing a whole bunch of pre-processing normalizations. Is very simple using this syntax to, for example, test many different scalars, many different pre-processing nodes, because they always have this, all of them, like no matter whether you're scaling min-max, you're using z-scoring of your data, you are doing whatever fancier pre-processing normalization, you will always have, like all of those possible transformations are all represented by objects that have a fit method and a transform method. So it's very simple to, for example, write a loop where you test one after the other different preprocessors, and you evaluate the effects over your data analysis pipeline. And the same for principal, like for dimensionality reductions. Like here we will look at the implementation of like how to do principal component analysis, but there are other decompositions and like dimensionality reductions procedures that you might want to use on your data that always have the same interface, even if the class that implements them is different. So I don't know how many here knows what, like have a rough intuition, not necessarily a thorough mathematical understanding of what PCA is. Rough intuition is fine. Okay. So with principal component analysis, the idea is we have some data that clearly shows some correlation, and we want to find what are the, like if we can find some axes, some orthogonal axes in those data that maximize the variance explained by each axis. Now, there are reasons why we might want to do this in like many different contexts. It's a very long topic to go into details, and this is not a statistical course, so I won't go any farther than that. But yeah, the idea is we want to find the main axis of variations over this data set. So in this case, the original data set is a data set where each data point has a value over two different variables. You can imagine that each of those dots is, I don't know, the length and like, I don't know, like electrophysiology, the amplitude and the duration of a spike, or like any kind of data that can be described by two different quantities, okay? And there is some clear correlation between those two quantities. And every time we see correlations in the data, we might say, okay, maybe instead of using two numbers to describe this data point, if I were to be using only one number, I could still capture a lot of what's happening in that data, and I can compress the representation of the data by a factor 2, because instead of carrying two numbers, I'm just carrying one numbers, because I can see that like there is not that much fluctuation over there. So if I know where a point is along this axis, I basically know everything that there is to know about that point. That's the gist. And yeah, this is like, mathematically, this is a procedure that requires some like linear algebra, but like we don't care about that. We use, we just go to scikit-learn and we read in the documentation, and we find that there is a PCA class that can be used to represent, like to perform this decomposition. and it has the same kind of vibe. So PCA is not a function, it's a class, and I have to, before computing the transformation, I initialize an object that describes that step of the pipeline. In this case, PCA is a transformation that can accept a parameter, which is the number of components that we want to keep, for people who knows how to like what PCA is. In this case, I'm just setting it to 2. And yeah, and after we have created this object, the syntax is yet again just this, I'm scaling the data because for computing PCA, we want to compute it over scaled data. And to actually find those components is as simple as just calling the fit method over the data matrix, okay? And yeah, one thing that we look at after computing PCA is the variance explained by each of the components that we have found. And we can see that actually the first component explains a large majority of the variance for this kind of data, which is reassuring. And yeah, we can look now all the things that we might care about for this transformation, which are the components that we actually found and the transformed data in this new principal component space, can be found as either calling functions from this object or looking at attributes of this object. And the idea is everything, all the parameters that has been optimized by this node will be found as attribute of this object. So when we compute principal component analysis, we take those data and we compute what are the optimal directions over which the new components have to be defined. And those new optimal directions are something that we have fit to the data. So if we want to look at them, we will find them as attributes of the object. So, I mean, this is confusing if you don't know the details of PCA transformations, but this is just the plot that I was doing before, where I also visualize what are those optimal directions that maximize variance explained. I just care for you to know that those which are kind of parameters to the for the transformation, I am retrieving them as attributes from the transformation object. And if I now want to actually transform my data in this new in the new space, I have exactly like for the scalar, I have this transform method where after I have feed the transformation, I now apply the transformation for some data points. And the same concept applies here as to the pre-processing steps. Like sometimes I can find principal components on some data, and they want to transform in that principal component space some new data. So actually splitting these fitting and transformation steps of the pipeline allow me to compute the parameters for some transformation on some data, and then use that transformation on a different set of data that I'm using. So in this case, I'm actually applying over the same set of data, and this is how my data look like in this newly defined principal component space, where one axis is actually the axis, like basically it's PCA are rotations. So this is just rotated so that the direction of maximum variance aligns with the first dimension, like the x-axis. Yeah, I'm not sure why this comes after PCAs, but this is usually something that we do, like is also part of the pre-processing. Many times when we are computing the, sorry, I think it doesn't make sense to talk about this here. Let me move it after. No, let's just talk about it here. So many times as I mentioned at the beginning, for these machine learning pipelines, we split our data into train and test data, because if you imagine you want to, I don't know, build a regression and you really want to know how good that regression is, you don't want to risk overfitting your original data. And so everyone knows here what overfitting is. rough understanding. So basically, if I give you 5 points, you can always find some, like, they look roughly like a linear distribution, but there is some noise. If I tell you, okay, you can like fit a function to those data, your intuition is I want to fit a line. But if you allow for enough parameters, the function that you can end up fitting is a very convoluted line that goes through all points, but is very bad at predicting new points from the distribution. And so to avoid this, which like this is called overfitting, and to avoid this, usually what you do is, instead of looking at the 5 data points that I gave you for looking at how good the function is you for example, you take out 2 of those points, you fit a function over the remaining 3, and then you look how far the function is from the last 2 points over which the function were not trained. So the function cannot do a convoluted path through those 2 new points, and the idea is with this left out data, you can really assess the performance of your optimization procedure better than just optimizing everything over the whole data set. And this is something very important that like you should keep in mind, like no matter, like people use it, is paramount for like if you do neural networks, like there is decisive, but even for simpler statistical like regressions or classifications, is always like is a very common and very important thing to keep in mind. And so many times when you have one of those classification pipeline or regression pipelines where you're looking at like a lot of data and you are regressing a lot of things, many times what you do is you actually want to iterate, like you want to find different partitions of your data. Like you do one time you're splitting in train and test and you compute your regression. Then you do another time they split in train and test and you compute your regression. And in this way you get a general sense of how good your pipeline procedure is, not on that specific split of train and test, but overall over all the ensemble of all possible splits. So imagine that, like, I don't know, here I have a data set where, again, like is a lot of points that come from different clusters, and those clusters can be like whatever. And like is a 2-dimensional data that I'm scattering in X and Y. And you can see that points are grouped into all those different blobs. And for example, with this data set, something that you might want and we will be doing later is to do is clustering. So find what are all the Gaussians that produce those different blobs of data points. And yeah, what we actually want to do though, before start clustering, is to split this distribution in a train and a test set. This is something that we could be doing manually, like we could manually specify, okay, split, like we want 20% data to be put in the train group, so like use random to produce a number of indexes that extract that data, and we keep those data for the train group, and extract the remaining points, and we keep those for the train group. But there is actually a very convenient train test split function implemented in scikit-learn that extract in this case, the data is an X and Y, where Y is the cluster that we have to come up with. And it's very convenient because, like, we cannot go into that detail here, but if your data is, I don't know, stratified over some variable, like there are many things that you might want to optimize when you're doing this split in train and test, which can be like way more complicated than this naive view that I'm giving. And in this train test split function, you already find all of that implemented. And in this way, we have a group of like the X data and the corresponding cluster number, like number of the blob where it comes from, and the test data and the corresponding number of the cluster where they come from. And like in this case, I was splitting them into like 80% is train data and 20% is test data. So you have those 2 blocks of data points that come exactly from the same distributions, like because they're just drawn from the original data. And I can do whatever, optimize whatever clustering procedure over those train data, and test the goodness of this training procedure over the test data. yeah, and there are also tools to easily iterate over, like, we can skim through this, but the idea is you can just iterate very quickly over different splits in train and test of the data. So yeah, we were talking about clustering, and yeah, so in clustering the idea is we have some, like when we do regression, we have some, we want to optimize some line, some function that predicts some quantity on the basis of some other quantities. When we do clustering, the quantity that we want to predict is actually like the identity, like we assume that our data come from different distributions, and what we actually want to predict is the identity, like from which of those distributions our data point was coming. So in this case, I'm again generating with some more noise some of those blobs, which are our data points, and we want to, like, the color here represents the blob from which each data point was from, one, probably the most common algorithm that we can use for clustering is this algorithm called k-means, and it finds an implementation in the module of scikit-learn that is like quite intuitively named scikit-learn.cluster, and the gain follows always the same syntax as the rest of the nodes that we have been seeing. So like we don't care about the details of how k-means is implemented, but the idea is we will fit this k-means algorithm over some over some data, and we will predict the goodness of the model, not from the trained data over which we train the model, but over some new test data. And so the idea is we can now compare the actual, like in this plot here, you can actually see the original cluster identities for the data points that we were supposed to classify. And on the right, we actually see what we actually, like the clustering that we came out up with. And I mean, this is k-means clustering, so like it's a very kind of basic, linear, like super simple clustering method that doesn't do a very good job where those distributions are pretty close. So like it won't get any better than this, but in general, like even with like much more advanced like data sets where you have many more dimensions, you perform linear, nonlinear dimensionality reductions, and you use other kind of more advanced clustering methods, the overall gist and like pipeline is always the same. Like you feed the data over some split of train and test, and then you classify, you train the classification over some train data, and then you test the classification over some left test data. And yeah, final thing where I will ignore Matteo's comment, and I just want to mention that like when you, like sometimes you, at least it happened to me, like I knew that there were implementations for like clustering of whatever kind, and I started tinkering with clustering, and I came out with, I don't know, a classification, or like with linear regression or multilinear regression, and I came out with some regression, and then I asked, okay, how good this regression is, and I start implementing by myself all sort of methods for, I don't know, try to look like the bootstrapping, like the Monte Carlo thing that we were doing at the beginning, or like any other kind of hacked my own methods. Consider that for many of those problems, people also have thought of very thorough and precise methods for measuring the accuracy of your whatever classification or regression procedure. And in scikit-learn, actually, you find many of those. So I don't know. One of the most naive, like simple first-order checks that you can do for a classification problem is the so-called confusion matrix. That is a matrix that tells you, like compares which cluster a data point was, in which cluster we have put the data point, and tells you how, like, the more values are on the diagonal, so they were actually in cluster 0 and we have put them in cluster 0, the better our classification is, the more noisy this is, the worse this is. And like there is a simple function called confusion matrix that we can use for computing this matrix, which is like the one visualization that we want to do if you are doing clustering like we were in this example. But there's actually many other kind of quantification methods that you can use for also different kind of problems that you might be using scikit-learn for. And yeah, you should just check them out. But in general, like basically everything that you might want to look for any of those kind of more advanced machine learning problems, you should, like in general, you find them implemented in scikit-learn. And yeah, there is the next practical. And yeah, Matteo, here, let's give this satisfaction to Matteo. When you're doing clustering, sometimes your clustering method does not necessarily come up with the same, like the fact of calling this cluster 0, this cluster 1, this cluster 2, and this cluster 3 is entirely arbitrary. Like those are just labels that I'm giving to the cluster. And so many times the clustering methods can have different numberings for cluster. Like maybe I cluster them and the cluster look good, but this is now cluster 0, this is cluster 1, this is cluster 2, and this is cluster 3. So sometimes you have to also match clusters from the original and the clustered data. This is so we can remove Matteo's comment. And yeah, there is a practical where you can at least start tinkering with some of those scikit-learn pipelines. Like there are many steps, but even just the first one would be good to try to get familiar with this logic of combining pipelines.